Hello friends, welcome to Pipeline 105. We are going to see pipeline design envelope in this lecture. When I started this Beyond Pipeline YouTube channel, many friends asked me why the title is Beyond Pipelines when you are covering most of the topics about pipeline design. So I told them that initially I will be covering pipeline design topics, but in between there will be some topics which are related to beyond pipelines, related to other disciplines or process, material, or maybe some other pipeline integrity related things. A lot of things are there in my kind of a wish list, I can say, so that by adding those topics, the whole arena around pipeline will be covered. That's why the title Beyond Pipelines. And today's lecture is going to be one of such lectures where it is not exactly the pipeline design, but it's about the other factors that influence the pipeline design. And that is what is covered in this pipeline design envelope, lecture number 105 of Beyond Pipelines. So I hope you will like it, and let us start. So any object that we see has got a certain design capacity. So before going to the pipeline, I would like to explain few very general day-to-day examples so that you can easily understand what I am talking about, the design capacity. Let's take an example of a chair. When we buy a chair, somewhere in some corner of the seat, below the seat, the loading capacity of the chair is written. It is suitable for weighing up to carrying the weight up to 200 kg. You see also in the lift that this lift is suitable for carrying 6 person or maximum 1000 kg. So the chair also has got specific loading capacity. We buy AC air conditioner, we see the tonnage of the AC, like half ton, 1 ton, 2 ton, depending upon the room size. If we buy a car, we normally check, when you ask your friends what is the engine capacity, and it is said that 2.4 liter or 1000 cc, 2000 cc, 3000 cc, 3 liter, like that. If we buy utensils, then nowadays we have started seeing at the bottom of the utensil it is written whether it is suitable for microwave or not, because nowadays we are very regular users of microwave and sometimes dishwasher. So such design indication is given. So what is the meaning of it? That these material or these objects are designed for certain capacity, and you need to ensure that you follow it within that desired capacity, so that it goes well for the required service. Similarly, any piping system or any process facility or oil and gas facility will have its design capacity. You decide the design capacity first and then design the system for that desired capacity, and as long as you operate the system within that design capacity, you should not see any failures. So we say upsets happen when the certain parameters exceed the desired design capacity, and upsets can always happen, but we also overcome them by keeping certain ways of some kind of a safety norms. So hope you must have understood now that defined design capacity is very important for any object, and similarly for oil and gas facility or a pipeline or a piping system. We have seen in the past lectures about how to design the pipeline thickness based on design pressure and temperature. I have also explained you the hoop thickness, the longitudinal pressure thickness, and the equivalent stresses, the code compliances. A lot of things are being discussed in this series so far. Now we'll see what are the set of design conditions, okay, which are equally important for any system. So in addition to pressure and temperature, there could be some other factors that may influence the pipeline system design. We are going to explore a set of key parameters often called as design envelope that will have a decisive impact on a design of a pipeline system. It will have techno-commercial as well as environmental impact on our decision. Okay, so these parameters are very important. Like I gave the example of capacities of certain day-to-day objects. Similarly, it's not just simple capacity in any particular manner for the pipeline or pipeline system or oil and gas facility, but there are so many set of parameters required to be defined and ensured. So this is what we are going to see in this lecture. And as I said, when the pipeline system is operated within this defined design envelope set of parameters, then it should not fail during its design life. We are also going to see what is the meaning of design life. So let's proceed with the seeing the design envelope further. In this lecture, we will explore these key parameters that decide the design envelope of pipeline system. Please note that I am always using a word pipeline system. I am not saying a pipeline or a pipe, because pipeline cannot be considered independently. As as we have seen in the past lectures, pipeline is a means of transporting the fluid from one location to other location. So unless you define the parameters and the facilities of that upstream location and downstream location, pipeline system as such cannot be defined. So pipeline alone has got no entity. Okay, it is always required to be defined with upstream and downstream systems it is connected with, or the facilities it is connected with. The source of pressure, temperature are mostly governed by the connected stations, upstream and downstream facilities, like wells, pumps, compressors, heaters, slug catchers, storage tank, etc. We have seen in the field development lecture that from the well a flow line is connected to the gathering system. From gathering system a bulk line is connected to the process treatment facility. From process treatment facility a pipeline or export line is connected to transport the crude oil or treated gas for the export system, for the shipment or for the further use of the natural gas for the energy industry or the petrochemical industries and all that. So pipeline is defined always as a system, along with its upstream and downstream facilities. It's very important to understand that. And design envelope is therefore defined for the entire system, which includes a pipeline and upstream and downstream station facilities. Okay, sometimes it could consist of a multiple pipeline networks, because sometimes there could be a distribution network of a pipeline where multiple lines are connected together, and that also I have explained in the past lectures. So you must have understood now that design envelope is not just for a pipeline itself, but it is pipeline system. So we are always going to see a word pipeline system. So let us see what are the parameters, key parameters that we talk about will define the system design envelope. Like for chair we considered the weight, for utensils we considered maybe the temperature for the microwave oven, for air conditioner we considered the cooling capacity or tonnage. Similarly for pipeline system, it's not just one, but there are multiple things which are important. These key parameters are summarized here. First is design pressure. It will have again max and mean, maximum and minimum design pressure, because maximum design pressure will decide the hoop thickness. Minimum design pressure will also matter from avoiding the collapse of the line due to external pressure or vacuum conditions. We have seen that in the past. Design temperature, again max and mean. Maximum design temperature will have the impact on the strength of the pipeline. And when we have already seen, when we consider the thickness, we have to consider the temperature correction factor, which influences the the SMYs, or the material strength, and accordingly the thickness of the pipeline will vary. Similarly, minimum temperature will have some impact on the some kind of a impact, might have some cracking of the pipe if there is external impact happening to that. So it might have some detrimental effects on the pipe structure. So minimum temperature is equally important. Design life. So whenever you buy anything, you will have a desired life of that. You will never buy a car to be used for 50 years, correct? You will always consider that, okay, I will use it for 10 years. It becomes obsolete by then, because the new technologies, new cars will come in the market, and I will replace it with the new one. Similarly, any facility or any pipeline system also is defined with respect to certain design life. Though considering the kind of a capital investment and the efforts required to replace it, it's not like simply like buying a car and selling the old car. So considering that, there are always means and ways to extend the design life of such high capital investment kind of system in the in oil and gas industry. So we always will see that in further lecture. Fluid types, the we have seen in the past lectures about field development and types of pipelines that pipelines are meant to transport various types of fluids. It can be gathering system fluids, where the crude is taken, multi-phase crude is taken from the wells reservoir to the gathering system, then to the treatment plant, then the fluid is treated. It can be separated, liquid, gas, water, impurities will be separated, and then they will be individually transported, exported. So there are different types of fluids, and each type of fluid will have a lot of impact on the design. So if you are designing a pipeline to carry liquid, then you will have certain process conditions to be followed. If it is a gas which is compressible, then there will be again certain different process parameters and hydraulics to be considered. So the design of pipeline, process system design of pipeline has got a lot of influence on the basis of what fluid it is going to handle. Sometimes some pipeline might be designed for carrying multiple types of fluids. Then such set of design has to be considered. Like it might carry multiple, like sometimes it will carry stabilized crude, sometimes it will carry unstabilized crude, sometimes it will carry liquefied gas. So in that case, some pipelines can be designed for multiple products as well, but its process system design has to be accordingly tuned. Design flow rate and fluid velocity plays very important role, because basically when we say a pipeline sizing or hydraulics, what we do is we consider what is the flow to be handled through the pipeline, capacity, flow capacity, and then uh, the pressure difference between upstream and downstream, and the velocity will decide the pipe size. Uh, so you can imagine that the sizing of the pipe, which is a process design part, will depend on type of fluid, design conditions, design flow rate, fluid velocity, and the upstream downstream pressure difference. So design flow rate and fluid velocity plays very important role in pipeline design envelope. Fluid velocity will have you know the type of flow might vary. We have seen that the laminar flow and turbulent flow, and then there are certain effects of such flows on the pipeline corrosion, internal corrosion of the pipeline, as well as sometimes very high velocity with the fluid carrying some impurities might have some kind of a erosion impact as well. So fluid velocity plays very important role as well in the pipeline design, and it's part of the very much part of the design envelope. The material selection of a pipeline and its various components and upstream downstream facility also plays very crucial role. And we are going to see the details of the different materials, and then obviously the fluid that is going to be transported through the pipeline and treated in the facility will have the corrosive nature, some other types of corrosion, or the other detrimental effects can be there, and accordingly we have to decide the corrosion allowance, and we have to select the material suitable to those properties of the fluids. Let us see now all these parameters what we have seen so far individually, key parameters, so that we can understand them better. So the first and foremost is design pressure, because we have always seen that the pipeline thickness is always selected based on the pressure. So we have to withstand the pressure, okay, in the pipeline system design. So whenever we are going to see these key parameters defining the design envelope, what we are going to see is obviously the source of that parameter. So source of the pressure or pressure source is going to be like reservoir pressure for oil and gas well. If it is a facility is transporting the liquid from one end to other, then it could be a pump or a compressor to be used so that the fluid can be transported, the pressure difference can be created to transport the required volume through the selected diameter of the pipeline. So all these pressure sources, what we have seen, will decide the minimum, normal and maximum operating pressure that the connected pipeline system can encounter. Then what we do is, as I said, we have to ensure that these parameters will remain within the design envelope. So if we are designing the pipeline for certain pressure, if we are selecting the thickness for certain hoop thickness selection, then we cannot allow the pressure to go beyond that. So for that, what we do is we always provide overpressure safeguards in the system, so that whenever the source pressure starts going towards the upset condition, unanticipated conditions beyond the design pressure envelope, then the safeguards will work. Something like relief valves or instrumented protection systems, where the high pressure will be detected by instruments, and then it will trip a valve so that the flow is cut off. And upstream of such protection system or valve, locally only can be designed for high pressure, which will be limited to only shorter lengths, but the majority of the lengths can be then designed for reduced design pressure, because the safeguards will work. So the settings of such overpressure safeguards will normally decide the design pressure, because the safeguards are going to ensure that the pressure will not exceed the design pressure. So it is decided on the basis of such safeguards as well as from the pressure sources. If we can design the pipeline or the system for the full source pressure, then we don't have to. So in most cases, the system downstream of the overpressure safeguard can be designed for practical and economically viable lower design pressures. So as I said, if the upset condition can happen, then it will be detected with respect to the safeguard at very close to the pressure source, so that only up to that section will be designed for high pressure, and downstream system can be designed for lower pressure. By doing that, we can reduce the thickness of the pipeline and equipment, and the whole system, station as well as the pipelines, and economically it will become like less capital investment requirement. So the overpressure safeguards always are important, and they play a detrimental role in the kind of the economics of the oil and gas facility implementation. Yeah. If the source pressure itself is very low, it is within the practical limits, then the whole system can be designed for the full pressure. So there is no upsets expected in such case, and in that case it will be considered as a fully rated system. Fully rated system is always ideal because you can't expect any kind of a overpressure scenarios, and related incidents cannot happen. So it is ideal situation, but whenever the pressure sources are very high, then from the project economics point of view, we have to implement the overpressure safeguards, and then using that we design the majority of the system for lower pressure or underrated system it is called. That way we can reduce the overall capital investment. So as I said, the safeguards will help the economics of the project. Now let's move to the second important parameter of design envelope, which is temperature. So design temperature, any system similar to what we saw in the pressure source, the similar sources will be there for the temperature. It can be reservoir fluids, can come with high temperature, or the pump or compressor can have the certain temperature values at the export at its exit, or the sometimes there could be a heater or cooler in the system, process facility, and cooler will cool down the fluid to certain temperature before it enters the pipeline, or heater will heat the fluid to certain temperature before it enters the pipeline, and that will have the process system design impact of the pipeline. So process system design or pipeline sizing, the flow parameters, and design pressure and temperature will be decided based on at what temperature the fluid enters the pipeline. And for certain material selection of the pipeline, certain temperatures might create a limitation. Therefore, the maintaining the temperature within the desired design value becomes very crucial. So what we do is all based on the source temperatures. Suppose there is a cooler, then cooler set pressure at the exit. If there is a heater, then heater exit temperature, cooler exit temperature, heater exit temperature will decide the max operating temperature of the system. And we normally, there is a thumb rule to add 10 degrees as margin on top of the max operating temperature value to derive the design temperature. This 10 can be reduced to lower side also, but thumb rule is to consider 10. There is no set criteria for that, but normally people consider 10 as a adequate safety margin. So as I said, the necessary safeguards are added to ensure that the downstream system will not encounter more than desired temperature. As we have seen, it is very important from the material perspective, and sometimes and most of the times from the flow perspective as well, because it may change the flow parameters, and that might have some impact on the flow capacities and pressures. So in such cases, the settings of temperature safeguards will decide the max operating temperature of the system, and then by adding the required margin, the design temperature will be selected for the connected pipeline. Let's move to the design life, which is very important, that for what design life we are going to design the system. Typically, you will always find that 20 years design life is a benchmark considered for any new system design. We will see when I started in this industry, I was very curious that why 20 years benchmark, from where it came. So now always you always find the design life of any new facility is 20 years. So out of that curiosity, After doing some review of the standards and some requirements, I realized that the 20 years came from a certain criteria. Let's see that. Okay, so this is a magic number of 20 years. So why 20 years? So whenever you do a mechanical design, for the thickness calculation or its mechanical design criteria is applied, the fatigue factor is applied. So whenever the fatigue factor exceeds 7,000 fatigue cycles, then the fatigue factors reduces below 1. So that means it will have an impact on the thickness or system design. So up to 7,000 cycles, fatigue factor is 1. So that means fatigue has got not much or no impact on the thickness selection. That means economics of the system. So these 7,000 fatigue cycles are converted into design life. How? Let us see that. So if you consider the most conservative cycle, see the fatigue cycle of a process system, oil and gas system or petrochemical system means the system will have to see either one full pressure cycle from high pressure to low pressure, or temperature cycle from high pressure to low temperature, high temperature to low temperature. So such, or sometimes the external forces like wind or some kind of vibrations. So we are not going to see that at the moment, but we will see the key parameters which are part of design envelope right now. So one full pressure cycle and one full temperature cycle, it's not very commonly going to occur. In the process system, in a pipeline, you are never going to see the pipeline will be pressurized and depressurized so frequently, or temperature fluctuations will be so high that pipeline will see max temperature to minimum temperature so frequently. But in terms of fatigue, one cycle means it sees one high pressure to low pressure range or one high temperature to low temperature range. So even if we consider the worst case, which is one such pressure or temperature cycle happening every day once, which is highly unlikely. It can happen maximum once in a year or 6 months, once in a 6 months or something like that. But even if you consider that happening once every day, then if you assume 350 days round figure for a year, then that means 350 cycles can happen per year. Into 20 years, if you consider multiply, then it will become 7,000 cycles. So how 20 years of design life, that magic number has come, is basically 7,000 cycles with up to which fatigue factor remains 1, divided by maximum possible cycles in a day, and then it is converted to 20 years. So it happens to be 20 years. So you will always find the design life is always defined as 20 years. And once you understand this, you will start enjoying it. Pipeline design code like B31.8, as we have seen B31.8 and 4, which are globally the most commonly used codes. They apply the fatigue factor in similar manner, but they have, based on the design factor and certain other parameters, a specific formula is given, and you have to apply that. However, typically the benchmark is still 20 years. You will see so many clauses in 31.8 which says that the 20 years or certain particular criteria, whichever is higher. So 20 years is still considered as a benchmark. By means of even though you design your system for 20 years of design life, but as I said, the highly capital investment is involved in the pipeline and all these facility installations. So it's not easy to replace the whole thing after every 20 years. So there are inspection and maintenance, regular inspection is done, maintenance is planned, and repairs are done for anything that is observed during inspection. And by doing it regularly, the operating life of the system, including the pipeline, can be easily extended beyond the design life. But if you just simply neglect everything, then the design life of 20 years or maybe lower uh, will be applicable. But for highly capital investment elements, you always do regular inspection and maintenance and then extend the design life. And there are many examples of process equipment and pipelines safely operating beyond its design life of 20 years. Even it has crossed 50 years in many cases. There are so many examples available. You might need to do regular inspection, repairs. Sometimes you need to replace certain sections of the pipeline which are corroding heavily. But by doing such localized kind of a thing, by taking regular shutdown windows and doing such maintenance and repairs, you can extend the design life to much longer than the original design life of 20 years. So it's very important. Now let's see the types of fluids. As I mentioned, the types of fluids plays very important role in the process system design, hydraulics of the pipeline. So what are the types of fluids we can see? We can imagine. So in incompressible liquids like water or stabilized crude. Then it could be compressible liquids like unstabilized crude, LPG, LNG. There could be gases like air, nitrogen, crude natural gas, treated natural gas, crude oil or gas or produced water containing impurities. So even though this is one of the three services above, fluid services mentioned above, but it can have some impurities, and I will talk about it when we go to the material selection. The impurities also play important role. System hydraulics or process design, the is will depend on all these different types of fluids. So for the flow capacity, flow velocity, overpressure safeguards, all these things, process system design will come in the picture. So the all these parameters, process fluid will type of fluid or fluid service, process service will play very vital role in the system design. The material selection, stored energy, hazard criticality will be heavily dependent on the type of fluid to be handled by the system and associated pipeline. So you can imagine that if it is a compressible fluid like or gases like nitrogen or crude natural gas, if we are compressing, we have to compress the gas in the pipeline based on its diameter to start the flow, to create the flow from one point to other. The differential pressure has to be developed. So that means the pipeline has to be pressurized to that pressure first, and then the differential pressure will create the required flow. So that means there will always be a kind of a stored energy in the pipeline. It will be, if it is a highly volatile fluid, and it can be considered as a live bomb, so you are pressurizing natural gas, which is which can be easily, gets ignited if it is it sees a fire source and oxygen. So if there is a so much gas you are pressurizing in a pipeline, then so much energy is getting stored in that system, and that's why the gas pipelines, highly pressurized gas pipelines becomes very critical, in terms of the hazards. So type of fluid to be handled by the system is very crucial in the overall system design, and pipeline is one of the critical component of that, which has to maintain that pressure, contain the required pressure and volumes. Pipeline size optimization also will depend on all these parameters. So you can optimize the pipe size, and once again it will correlate to the economics. So the lower the pipe diameter, lower the thickness, and lower the capital investment. So it becomes very important for the size optimization. It depends on these process fluids which the pipeline system is going to handle. Let's move to the pipeline materials. So the material selection, even though it is pipeline materials, but it's equally important for the upstream and downstream facility and its equipment and process systems as well. But we are going to focus more on the pipeline material part. So what are the different types of materials we can see for the pipelines? So it can be carbon steel, it will be bare carbon steel, internally no liner or no coating. It can be stainless steel or duplex stainless steel. It can be glass reinforced epoxy, typically known as GRE pipes. Okay, can be used for pipeline. Carbon steel with internal polyethylene liner or P liners, it is called. So we can have a carbon steel pipe. Inside there will be a P liner. So the corrosive fluid will not come in the contact with the carbon steel. So carbon steel pipe will give basically the means to withstand the pressure as a backing, and then P liner will take care of the corrosive kind of avoiding the contact of fluid with the so P liner is not going to withstand any pressure. It's basically backed by the carbon steel pipe. Flexible pipes made from polymers, they are typically known as LRTP. These are like hoses, but they are specially fabricated design hoses with reinforcement. So those are used for the temporary means, like you want to quickly connect something just for the sake of testing. You don't have the assured kind of a flow or performance of certain system, but you just want temporarily check, during the testing part. In that case, these lines are used. By doing a lot of research and new developments, new technology, nowadays long duration flexible pipes or its design life is getting extended. So the use of flexible pipes is increasing in the oil and gas industry these days. System design will depend upon the pipeline material selection to great extent, as I explained earlier also. So let us see some examples like CS pipeline. If we are talking about the bare CS pipeline, then it will have the service fluid will have some corrosive impact or corrosion effect on the pipe surface. So that means as part of your routine maintenance and inspection, you need to keep removing that liquid out of the pipe. If you don't do that, then the liquid separation happening in the pipe will have a kind of stagnant liquids sitting in the bottom of the pipe along the pipeline. As we can imagine, the pipeline will have the profile, it is going to follow uh, the uh, the earth profile. We are going to take the line, install the line from one place to other place. Along that there will be high points and low points of the grade profile. So pipeline will follow that grade, so there will be always high points and low points getting created along the route. At such low points there will be stagnant liquids getting stagnated, and those will have detrimental corrosion impact on the pipe. So it will start the corrosion at the normally 6 o'clock position in the pipe, and to avoid from such things from happening, we need to keep removing these liquids regularly from these low points. For doing that, we have to do the pigging. The pig has to be passed. We have seen the pig trap and how the pigging is done. We have seen in earlier lectures as part of the pipeline system components. So when we drive a pig, it will remove all this liquid from all these low points towards the downstream facility. But the problem is whenever you are going to do the pigging, large volume of liquid, which is called slug, is going to reach the downstream facility, and for that you need to have a handling capacity in the downstream facility. So material selection, when you are selecting the carbon steel large diameter pipeline, then you have to also design the facility. You might need a large capacity of a slug catcher or a separator in the downstream facility. So it's not just a pipeline. So its material selection has got so much impact on the overall system parameters, upstream and downstream facilities. GRE pipes, okay, so GRE pipes will have a limitation in terms of pressure, temperature, impurities, because GRE pipe is made from the glass reinforced epoxy. So you cannot, it has to be tested. It cannot be designed exactly like carbon steel pipe. Though there are, based on the research, there are design criteria and formulae developed, but still a lot of qualification is done for the GRE. So unless, and it is very difficult for the GRE to withstand very high pressure with very large diameters. So there, then of course, there will be limitations of the GRE pipes. So it has got limitations of temperatures, pressures. Temperature, of course, will have an impact on GRE because it is glass reinforced epoxy. Its strength will be reduced when the temperature goes up, similar to carbon steel. But here the impact will be much higher. So if there are impurities like sand, proppants flowing along with the fluid, like for the upstream facilities, mainly upstream gathering systems mainly, then it might erode the GRE pipe, and inside the GRE pipe we can't do like intelligent pigging kind of a thing, or UT inspection, by which we can uh, we can estimate what is the loss of thickness. So it becomes even more difficult for the GRE pipe because it remains kind of an unanticipated thing. So for GRE pipe, the fluid surface carrying impurities, erosive impurities, becomes a high risk. Uh, I already explained that this is erosion threat is always becomes important for the GRE material. Stainless steel lines or duplex lines might have good corrosive properties against certain fluids, type of fluids, but chlorides and sulfides and H2S services might have uh, uh, sulfide stress corrosion cracking kind of a these materials are highly susceptible to such kind of a type of corrosions. So they have limitations. So you can't use stainless steel pipes for the highly saline water, or high H2S services where high stress induced corrosion can become a problem. So every material has got some limitation, and accordingly the system design has to be done, and the material selection plays such an important role in the overall system design, and that's why it is one of the important factors of system design envelope of a pipeline. So we have seen the key parameters of design envelope, how the design envelope is defined, and all these parameters need to be properly documented, okay, and followed during various stages of the project. We will try to see various stages of the project implementation, starting from the select, concept, then the define, execute and operate. But this design envelope is, once it is defined, then from that stage onwards, for all the remaining stages of the project right up to the operate, it has to be properly recorded and followed. So we'll just try to see quickly in which key deliverables the design envelope has to be recorded and followed by various teams of the project, and even in the operate phase. The first is project design basis, in which the project design basis basically defines the scope of the project, the background of the project, and the design envelope and design methodologies. So design envelope becomes part and parcel of project design basis, where the design team will refer to it and design the system accordingly. Material selection report. As I explained earlier, the material selection or selected material of the system, including pipeline, becomes very crucial for the overall system requirements. So material selection report has got very important role to play, and pipeline design envelope is very crucial for correct material selection, and they are basically interrelated. Then once you have done the design envelope definition, you have defined the required project scope, requirements, and selected the material. Then based on the selected material and based on the design envelope, it becomes important to maintain the pipeline, as I explained, maintain the pipeline as well as the facility, so that you can ensure the design life first and then extend the operational life beyond the design life by doing the regular inspection, maintenance, and repairs necessary. So all these requirements are recorded in the corrosion management framework, and therefore as part of the corrosion management framework, the pipeline design envelope is the first and foremost thing to record, and that forms a reference for the facility and pipeline to be operated and maintained. And pipeline maintenance manual, where the pigging frequency is, chemical inhibition requirements, and all these kind of important aspects of related to pipeline will be defined, which also has got important reference in with respect to design envelope. So design envelope plays very important role in all these kind of key deliverables, which are developed and followed in the entire project design cycle right up to the operate phase. As I said, by means of regular inspection and maintenance, the operating life of a pipeline system can be extended much beyond its originally defined design life. So design life originally is 20 years, but we can extend the life of capex intensive systems like pipelines and equipment and processing facilities much beyond the design life. And as I explained earlier, there are examples of successful operation lives of 50 years, whereas the design life was originally 20 years. Not only for initial design of the pipeline system, but also for achieving longer operational life, as I mentioned, the knowledge of design envelope becomes important, because then only you will understand the key parameters to be ensured, maintained throughout the life, and then for the extended life of the facility by operations and maintenance team. So if they don't know or don't have the adequate knowledge of design envelope of the system, then it will become almost impossible for the operations and maintenance team to ensure the required measures to be implemented for extending the design life. So I believe you have understood the importance of design life. It was kind of a associated lecture related to pipeline design, but it plays very important role, and that's why it is covered under Beyond Pipeline series. Based on this, we will also see the different types of pressures, like operating pressure, normal operating pressure, maximum operating pressure, then design pressure, then the maximum allowable operating pressure, then maximum allowable incidental pressure, and all these parameters will be defined and explained in the further series of these lectures. And for that, this lecture was very important. It sets the kind of a background for these details which we are going to explore further. Hope you understood the importance of design envelope and various key design parameters related to pipeline design. That's it for now. See you again. Bye bye.